Okay, so like I was saying earlier, it will be comprehensive, but it's not going to be that long. I, as of right now, have 6 problems for you and an extra credit. They shouldn't be that long. I've tried to keep it to be about an hour long. If you guys can have more time if you want. I'm not going to stop you at an hour, although you will. Do you guys have to go to co-op after?
We do.
You do. Okay, so yeah. So you know we often run over, and so however much time, that's cool. So we're going to go over this in just a second. The first thing I want to say, I'm going to read exactly what I've written at the very top of this. I think we've done this once before. This bears repeating. Okay, so here we go. First off, no calculators. Exact answers only. Obviously. Now, here we go. You must reduce all computable inverse trig functions to their output values. I'm going to read this exactly, then I'm going to show you exactly what I mean. For example, since arcsine of 1 is computable and is equal to, what is arcsine of 1?
Pi over 2.
Yes! Good. Okay, good. If you got nothing else from this class, hopefully you got that, right? You plug in a 1, you get out a pi over 2. Why is that? Well, because of the way we chop up sine, right? Here's sine, it does this. We decided to chop it up right here and right here. And it's the case that when you plug in pi over 2 into sine, right there, you get out a 1. And so the inverse is the opposite of that. You plug in a 1, you get out a pi over 2. Okay, we're all on the same page. Since it's computable and it's equal to pi over 2, a question whose answer that you found to be arcsine of 1, if you answer that way, you will get points taken off. That is, since that is computable, you know what the output is. And so your final answer would be this guy right there. Okay? Okay? Now, however, if, because I said exact answers only, it might be the case that one of your answers is this. Do we know what that is? No, we don't. And here's the thing, right? Whatever goes in here, if it can't be done with one of these triangles, right? 1, 2, root 3, or 1, root 2, 1. If it's not the ratios of one of those guys, or 1, or 0, then we don't know what it is, right? These are really at least in our class, these are the only ones we've talked about. We could really get pedantic here and say, well, what about like sine pi over 2 minus pi over 3?
Oh, we can't do that.
Is that pi over 6?
Yes.
Yeah, so not that. How about pi over 3 minus pi over 6?
Yeah, we can do it.
We could do that by using the addition formula, or the addition and subtraction formulas and stuff like that, and then you could find an answer. I'm not talking about that. You're not going to run into that here. If you're taking arcsine of something, and it's not a 1 or a 0, or one of these, like 1 over root 2, or 1 over root 3, or 2 over root 3, or something like, or root 3 over 2, or something like that, then it's not what I'm calling not computable, and then this would be a sufficient answer. So one more time. This is not a sufficient answer. Bad answer. Good answer. This, good answer, because you can't figure that out, right? Another thing, what would this be?
7 pi over 2. Wait, no.
It's not possible.
Yeah.
That's right. Because can you plug a 7 into here?
No. Oh.
No, you can only do it from here to here. Similarly, that's like saying you plug some number into sine and out popped a 7. That ain't happening, right? So, okay. So just to kind of finish up what I said. For example, arcsine 1 is computable and is equal to pi over 2. A question whose answer you found to be arcsine 1 must be reported as pi over 2 to receive full credit. Since we don't know how to compute arcsine of 1/7, then arcsine of 1/7 is a sufficient answer. Everybody got that? Okay. So we're gonna go over a few things. I'm not really going to give you a blow-by-blow, but more of just in general the things that you're going to want to know. Of course, you should have expected this. Know your trig identities, right? Like, or rather, be able to verify a trig identity. If I give you one, right, you should be able to prove it. Now, I'll say the one that I have for this test, normally I have told you start on one side of it and operate until you get to the other side. You may or may not want to do it this way. The one that I'm looking at right now on your test. I've also said that you could do stuff on like both sides of the equation, right? Like, I wish I had something figured out. I'm sorry I don't have anything figured out for you here. But like, if I had something like this, 1 minus sine squared theta. If we're trying to prove this guy right here, I think I've done this right. Now you know of an identity that involves sine squared and 1, and you know what is this equal to? That's cosine squared, right? So I mean, what you could do, like I think you already know which identity. Like as soon as I wrote this up there, and you say the word sine squared and cosine squared, this right here should be going through your head, right? And so that's going through your head. And so on one hand, you might be really stuck. Actually, you can just do you just subtract it off and then subtract that off. That would work too. See, I didn't plan this out. And you'd get that, and that would be true. And so you could just start on that side of the equation, bang it out until you get to there. But my point is, like, another way you could do this is to just repeat this with everything, right? And just say, well, hold on. Like, I could do this type of thing. I could add this to the other side, plus 1 minus sine squared theta. And then that's equal to cosine sine squared theta plus cosine squared. That's true. Okay, and so, like, and on the test, if you do it in this order, that's cool too, but just tell me, like, what you could do, something like this, and say, since all of these steps are reversible, they go in both directions, not just in one direction. Each one of these, obviously, we just added things and used an identity. So that would be fine, but let me know either by doing these arrows that these are indeed reversible, and then say, okay, since this is true, like, since this, then this, or something, you know what I mean? Like, it's a test, so you don't have to go crazy with explanations and stuff like that. But there you go, right? Then again, if you're in the habit of just starting with a more complicated side, turning it into the other side, that's cool too. Although, I'm going to tell you with this one, you might want to just write, like, it's just, like, I'm looking at it, I'm like, oh, that's that. And you might want to just have that. It's not too hard. It's really not too hard, but at any rate. Okay, so, know how to be able to, there we go, be able to graph the following: sine, cosine, tan, cotan, secant, cosecant. Okay, and also be able to graph arc sine, arc cosine, and arc tan. For every one of these, for every single one of these, be able to, so we'll put it this way: 1, be able to graph all of those. 2, for each of them, or what I mean, like, this is, I'm just saying, like, in your graph, make sure that when you graph it, you identify A, maxima, that's the biggest values, right? B, minima, Maximums and minimums, right? The highest and lowest values. Not just the values, but also where they occur. So here, pay close attention here. Let's say I told you to graph sine on the interval, we'll make it easy, 0. So here we go. Let's say that I tell you to graph sine x on the interval 0 to 2 pi. Okay, we know sine starts here, comes down, comes back up. Okay, so maxima, this is a max value. Okay, so we're going to need to label where that is. That's 1. Not just that, also where it occurs. Where does that occur? Pi over 2. Okay, and I think I state this explicitly. Label maximum.
And the intersections.
So I put label the maximum input output. So this would be your maximum input output. And this would be your minimum input output. What is the output?
I think it's -1.
And what's the input?
3 pi over 2.
Yes. It's like, no. Yeah. Yeah, okay, yes. 3 pi over 2. And so, when we actually, and so like what this means, and we're going to do this absolutely next year, we're going to think about a max, like a max of a function is like an ordered pair. Or we're going to kind of think about it like that. But, I'm not, please don't, you can if you want. If you want to do it as an ordered pair, that's cool too. But it's like, the max, it's not just when you're talking about a maximum, you're talking about where it occurs. And I need on the plane here, I need 2 bits of information to tell me where it occurs. If I just say max value, then we're just talking about what's the output value. If I say where is the max, we're just talking about there. But if I'm asking for the max, I want to know where it occurs and what the output is. So both the input and the output for that. Everybody got me?
Yeah.
Okay.
And we need the intersection.
That's
Okay.
axis intersections. Axis intersections, right? So this one, and this one. So in this case, I'm guessing 0 for both the x and the y. In this case, right? If it were cosine, it would be a little bit different because it would be up here, right? And so there would be a 0 there and a 1 there, which also happens to go ahead and knock out the max problem, but anyway, right? Okay, and this one is what? Pi, this one is 2 pi, right there, okay? So the axis intercepts, if there are any asymptotes. So there are no asymptotes for this guy, but there are other asymptotes, right?
Yeah, and secant. Yeah.
For which ones? Actually, for all, tell me which ones of these have asymptotes.
All of them except the sine and cosine.
Yeah.
So tan, cotan.
So yes,
secant.
tan has that. Cotan.
Secant.
Secant.
Cosecant. And arctan.
Arctan, good. Arctan does have asymptotes, right? Because tan has asymptotes, and so when you flip it, right, arctan's going to have asymptotes too. Okay? All right, so that's be able to do this. Okay? You should be able to do each one of these in your sleep. I might ask you 1, I might ask you 2, I might ask you 3, but be able to just do that. And that's all the question's going to be, just graph these things.
So will it be like sine of 2 pi plus 1? Or?
That's coming up. But there will be a problem where I just say graph these. Because like at the end of this class, you should be able to do all of these. Like with all of this right here. You should be able to pull all of this information out. And I cannot tell you how important that's going to be in your future mathematical career. Like being able to just whip out a thumbnail sketch like I just did right here. Yeah. Yeah. Okay? Okay. Questions on this? Any more questions? Ooh, that in a second. Okay. So another thing. Be able to solve equations involving trig functions. Okay. Probably the most common one that just say it this way. You remember something of this form.
Yeah.
These bad boys, right? Like, yes, of course, you might have like a sine x equals cosine x, something like that. And if you had that, how would you solve that? What would you do?
You take arc sine. Well, wait, no.
Divide both sides.
Divide both sides by what?
By
Sine.
No, by
No.
cosine.
Yeah.
And then it's tan.
You
tan.
could do it either way. It's just that this right here
Yeah.
gives you that, which gives you that.
And then arctan. Or just.
And then arctan or whatever,
Yeah.
right? And so you could say, and what, okay, yeah, arctan of both sides so that we get this.
Which would.
Can
No.
you figure that out?
Wait, arctan. No, because.
That's where the S.
No. Yes, you can. It's
You
No.
better know what arctan
That's
looks
that
like.
pi over.
It's,
No,
It's
yeah.
what?
It's
pi over 2.
No,
No,
pi
pi
over
over
4. Pi over
Good,
4.
excellent. Because right, and this should be your question right here. Is like, what triangle can I get a 1 from with tangent? And so every one of these questions, this should either be in your mind, or if you write this on every single sheet, like if you just start with every piece of paper on the quiz, if you just write this at the top, that's going to help you. Because you go tan, or tan. Ah, that does it. It's that one. And so we know that tan pi over 4 is 1, right? Because that's opposite over adjacent. Therefore, this would be the answer that I'm looking for. Or is it? Because I might tell you to solve, give all solutions.
Oh, no, that was just one. Wait.
That's just one solution.
So then it'd be that plus pi times x.
Yeah, that's what I'm thinking. And what I would suggest you do is when you get down to this point right here and you're like, oh no, I gotta do all solutions. I would just say, well, so first off, you're not gonna draw that. that ain't happening. This is the thing from which you derived this. So let's look at this and say, okay, what does tan x look like? And you could pull out a thumbnail sketch and say, okay, well I know tan does this thing. And then it does this thing. And you're right, because it does work out to be, okay, so here's pi over 2, here's pi. We know that when I plug in a pi over 4, I get out a 1. And so what we're looking for is all of these guys, every single one of them, and I could say that we're off by how much? What's the distance from here to here?
Pi.
No, 2 pi.
No.
Oh, pi, yeah.
It's pi. This would be pi over 4 plus pi. And then the next one would be pi over 4 plus 2 pi, pi over 4. So I could say then for this problem, the answer wouldn't just be this. It would be pi over 4 plus pi times n, or n pi. And I'm not gonna, you don't have to do this, like where n is any integer. I know that if you use an n in this kind of problem, then you mean that it takes on all integer values, right?
Yeah.
Because it's not just these positive ones, it also works if you subtract off. So when n is minus 1, you're down here at pi over 4 minus pi. Pi over 4 minus 2 pi, minus 3 pi, minus 4 pi, and so on and so forth, right? Okay, so be able to do that. And this was like a very common one that we spent a lot of time on, where you have something like this.
You
How-
just substitute cosine equals x.
Yeah,
Cosine
or
of x equals x. Or a different letter, probably.
probably a different letter would be nice, right? So you have this type of thing. Now here's the thing though. Like, okay, so now what would you do? Because we're looking for cosine, right? So in other words, we're looking for z. And so you could just say z equals,
This is
it's what?
negative b plus or minus
There you go.
squared. B squared minus
Right,
4ac.
you could do this. All over 2a, right? And so then you say, that was z, so that's my cosine x.
And then
And then that's some number, right? Or it's probably 2 numbers, and so maybe it's like a 3 and a root 3 over 2. And first off, one of those doesn't make any sense.
Cosine of x equals 3.
Right. So you picked up an extraneous solution somehow. In this case, which. And then the other one would be the one that you care about. But oftentimes, right? What have I said since like last year? It's like that might be more work than you need to do, especially if it's I don't know, something like this. You could use a quadratic. You could use a quadratic here. But it might be easier, maybe, I don't know, to try to factor it. Yeah. Uh-huh. Yeah. That one's got to be a 1.
So just
I have a 3.
3 and 1.
Right? I mean, maybe it's
Yeah.
how else can you get it, right? So let's just see. Right? Plus.
So
it has to be
minus.
plus and plus.
Yeah, plus and plus.
It have to be plus and plus. And so on one hand, and so now what would you do? How would you get to the bottom of this guy?
What is
Say
two
3
equations?
cos equals negative 1 and cos equals...
Yes, so this means 3 cos equals negative 1, or in other words, cosine x is equal to, how about negative 1/3?
Oh.
Yeah.
Right?
And
Right?
then-
Because you set that equal to 0. This is what you're doing. You're saying, well, if that's true, if this is true, then this is true, regardless of what that is. Right? This is going back to last year, right? And so you bring the 1 over, and you have your 3 cos, divide by 3 to give you that. What does this give you?
Cosine of x negative 1.
Cosine of x equals negative 1. Okay? So now, what do you do? And let's say we want all solutions. So let me get rid of this. I'm going to rewrite these up here so we can have some more room, okay?
So I'll find all the places where both of those are true.
Exactly. And it is to your benefit, I think, to just draw these out real quick. That way you don't mess something up. It's so easy to mess these guys up. So we have these two possibilities. Now, on the first hand, we're talking about cosine x. I know what cosine x looks like, right? It does. It starts here, comes down, goes back up, goes back down, blah, 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 blah. Negative 1/3 would be down here. Somewhere. Let's go right there. Negative 1/3. And so, I'm looking for all of these guys. We'll come back to him in a second, because that's a bit more involved than this guy. This is really straightforward, because I could find all the solutions. They just occur right here.
So it's pi plus n plus pi times
Yes. 2 plus 2.
Okay, so you're telling me that this says that x is equal to
plus 2 pi.
pi, yeah, 2 pi n. Because plus pi n would get you right there. And that would bring you up there. That ain't right, right? So yes, the full period here is 2 pi. And so we want 2 pi n in both directions. Okay, so that gives you part of your answer.
Multiply that 30, 60, 90 by root 3.
Say again?
If we multiplied each side of the 30, 60, 90 by root 3, we could find...
Wait, so we take the 36, okay, so let's
By
take the
1
30, 60, 90, 1, 2, root 3. We multiply everybody by root 3.
Oh, that does work.
Does it?
Oh, wait, no.
How do you get 1/3 out of that?
Oh.
By,
So,
yeah,
looks like we're not gonna, looks like we won't, I'll say it this way. Looks like we won't be able to compute this one.
So we
What
just
are
say
arc cos of
the arc cos of
negative 1 negative
1
plus, plus.
Now this is where it gets hard.
It'd just be plus 2.
This is where it gets hard.
No.
Because it's
No,
not
no.
just plus 2 pi. Because if you take arc cos, now we also have to think about this. Arc cos is actually pretty easy to use, because if we think about what arc cos looks like, it starts here and comes up here. Okay? And so we have our 1, we have our negative 1. And so when I plug in my negative 1/3, oh yeah, and by the way, you better know where all of these guys are. I already told you, if you're drawing something, maxes and mins and all that, you have to know where they are, all intersections, all of that. So I plug in a minus 1/3 and I get a value that's between pi over 2 and pi. So that means that this thing, and yes indeed, if that's pi over 2 and this is pi, then my value should be somewhere between pi over 2 and pi. So this point right here is arc cos of negative 1/3, right?
Yeah.
Everybody buy that?
Yeah.
Like that's the symbol we're going to use for the output of this function, whatever it happens to be right there. Right, pi over 2 is down here.
Oh, but
This is some number, call it n. I don't want to use n. N is like an integer here. This is some number, call it z. Okay? So there's that number z. He lives right there, and he's that long.
so since it's
There's that number z. We're going to write that. What is that number? Well, it's whatever you get. It's the output. Z is the output of arc cos minus 1/3, right? So, okay. Also, so we know that if I could get all of these other guys here by doing the 2 pi trick, right? You just add 2 pi and you'll get all of these other ones here.
but then the
So I'm going to go ahead and just take care of that and say, okay, arc cos minus 1/3 plus 2 pi n. But now what about all of these guys?
it would be 2 pi minus arc cos.
I'm thinking, so that looks pretty good, right? Because, and I'm looking at symmetry here.
Oh wait, no. It would, oh yes.
Here's 2 pi. This distance is from there to there. That should be the same distance from there to there, right? By symmetry.
Yes.
Yeah? And so I could say if I go to 2 pi and minus off that value, then I should get to this point right there. And so my other one would be 2 pi minus arc cos negative 1/3, like that. And then that gives me this guy right there, and I can get all the others by adding multiples of 2 pi. Now, I remember when we were first doing this, I think Noah, you spotted a couple of them. You're like, you could write that a different way and just write it like. It turns out that like some of these are reducible. So 2 pi minus arc cos negative 1/3 plus 2 pi n. And sometimes it's easy to see like it's not so easy to see here, but like. There was one case where it turns out like we had 2 of these solutions and you could have written it as something plus pi. Doesn't work here, right? Like I think it worked with like tangent or something like that, right? Or whatever it was. We were able to reduce it down. We were able to take these two solution sets and combine them and write it in one nice nifty way. Don't do that. Like you're gonna waste your time trying to figure out, because we could try to figure out. Is there a better way of writing this as one thing? Maybe. Why waste your time, right? So, yeah. This is the answer to that original one that I wrote up there, which was what? 3 cos squared x, what did I say? Plus 4 cos?
Yeah.
Plus 1 equals 0. This would be all solutions to that guy right there.
There's a lot of steps in this
A lot of steps. Now, just one thing to keep in mind. Yes, lots of steps. Yes. One thing to keep in mind with this kind of thing is cosine. Can I get rid of all of this?
Yeah.
Okay. So, arc cos, I think, is a little easier to deal with than arc sine. Because let's say we had the same question. And we ended up with... Now we want arc sine. Let's say that we are doing like a sine x equals negative, let's call it root 3 over 2. Now here's one that would be computable. But if you think about what arc sine does, it comes up like this, comes down like that, and you say, oh, I'm sorry. So I want to draw this out so that I don't mess this up. Okay. And so I'm thinking, okay, that's sine x, and we want to know where are the outputs equal to minus root 3 over 2. Well, there's one there. And that, by the way, is the one that arc sine is going to pull back, right?
Yeah.
Arc sine's not going to tell you whatever this one is over here, right? He's going to tell you the one that's in his domain. What I'm saying in particular is arc sine looks like this. It goes from -1 up to 1, up to pi over 2, down to -pi over 2. And when I plug in a -√3 over 2, it gives me back this answer that's between 0 and -pi over 2. So in other words, the answer it gives me is this one. That's right here. Okay? Now, okay, so we got one of them, and we could see that. So I'm going to answer arc sine. So x is equal to arc sine -√3 over 2. Is that computable?
Yeah.
It's
Pi over 3, negative pi over 2. Or no.
It should be -pi over 3 because sine of pi over 3 gives you opposite over adjacent, right? But that's negative, right? And so it's the negative of it. Another way you could see it is to say, well, I know that's in like the fourth quadrant, right? And we're talking about something that's over 3, right? So it's that guy down there, which is 1, 3, 2, 3, 3 threes, 4 threes, 5 pi over 3. You could do it that way. Or you could say this is also -pi over 3. Either way, it doesn't matter. Okay?
Yeah.
Yeah? In this case, you could just do it that way. I chose something that has that, but let's just keep it like that. Okay? And say, okay, that's the plus 2 pi over n. Okay? What about all the others? Here's the hard part. Because that gives us this one, and all of those, and all of them back. Now I need these guys. How do I get to there with this? Now I'm going to put, here's a hint. Pi over 2, here's pi, there's 3 pi over 2, and there's 2 pi. I drew this one a little bit better. I like to think about these as distances, right? So let's look at this. If my thing is right here, okay, then the distance from there to there.
Oh.
But
Would be
here's the other bit that I need. I need to find this distance right there.
Let's do that.
so it'd be just pi plus.
Yeah, now here's the thing. Yes, so in other words, the distance is from there to there. But if I go pi plus this amount,
Pi plus that,
It's a
like that's
negative.
about, or pi minus.
yeah, okay. Do you see what Noah's saying? This is a negative number.
yes.
It is negative pi over 3. If I add it to pi, that brings me back to here.
Yeah.
So if I add arc sine negative whatever it is, then that brings me back that way. So I could say plus the absolute value of it, in which case you're absolutely right, and then we would say, you know, blah, 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 plus all that. Or I could subtract it. Knowing that it's negative, knowing that this is a negative value, I could go arc sine -√3 over 2 or pi pi minus this value
Plus 2 pi.
plus 2 pi n.
Yeah.
Yeah. Or I could go plus the absolute value. That's also fine. But I will love that. I will love it either way that you do that. And again, if this is you're not getting full credit. All right?
Yeah.
Because that's computable, isn't it?
It's pi over 4.
It's
No,
what?
negative pi. Negative pi over 3.
Negative pi over 3. That's what that is. Yes. Negative pi over 3. It is not 5 pi over 3 because of this guy right there. Like, you're right that if you plugged it, that will be one of the solutions. But the one that you found was this one right there, right? And you could be right by just saying, well, plug that in right here and then add all of those. And that works just great when this is computable. But when this is not computable, when this is something like 1/7, you need to be very cognizant of where this is, right?
Yeah.
Okay. And so, okay, any questions on this kind of thing?
I don't think so.
Okay, so finding solutions to an equation. All right, well, before we get into that, of course, you're going to have to graph some trig. And I already told you you're doing that. But you're going to have to graph one that's been like lifted and shifted and stretched. So let's do one that's been lifted and shifted and stretched. And so I'm going to tell you to do something like this. Graph y equals, and let's do, how about, make sure this isn't the same one. This is going to be bad. This is going to be really bad. Okay. How about, we're going to go +2. Graph on some interval. And
0 to 2.
yeah. We'll just leave that open for right now.
0 to like.
We'll figure that out. Okay. So what do we want to do first?
Just graph sine 3.
Just graph it without the shift
Well,
and
yeah.
the stretching. So just
4 sine
Okay.
x.
So you're telling me do graph. So first, what are we graphing?
4 sine of. Well, we gotta just 4 sine of 3x.
Yeah, we could do that. Or we could do 4 sine x. What's that going to look like? Where does it start?
It has, it starts at 0,
Okay.
goes up to 4.
Up to, yeah, there we go.
Down to negative
And-
4. And
okay.
then we'll repeat
And it
2 more
repeats
times. 2 more times.
2 more times in the course of until it
6
gets
pi.
to
2 pi. But
2 pi.
Oh,
Right. And so that means that this end point is what? Oh wait, you told me
Pi
it goes. I
pi
didn't.
over 2. No.
This is
2 pi
2 pi
over
over
3.
2 pi over 3. Good. Okay, so what you just did here is you just found that the period was equal to 2 pi divided by whatever that first number is right there. Right?
Yes.
That's what you did. Okay. Okay, so we did that. So that means that this point is what?
2 pi over 6.
There you go. 2 pi over 6
Or pi over 3.
and or pi over 3. Yeah.
Oh, yeah.
Pi over 3. And then that means that this point is what?
Pi over 6.
That would be 1 pi over 6. So 1 pi over 6, 2 pi over 6,
3 pi.
3 pi over 6, 4 pi over 6. You could write that as pi over 2 or 3 pi over 6. You remember when I did this, I was like, let's just find whatever that is, and then just write it in terms of whatever that denominator is. It'll make your life easier, etc., etc. Okay, so we're part of the way there. Okay, now what do you want to do? How do you want to deal with
Keep
this?
going until you get to 2
Oh, graph
Should we wait?
Yeah, I mean, yeah, that's gonna depend. So let's just say that I told you to grab, and you see, I'm trying to think about which way the shift's gonna go. So let's just, if, yes, I would agree. If we knew ahead of time where this was, I would say yes. Then draw enough of the period so that you could do your magic here, okay? Although, part of me wants to say, and I think this is how I told you to do it in class, is that just work with one period until you get to the very last part and then extend your period as much or as little as you need. And so I'm just going to work with one full period right now. Now what do you want to do?
Do the shift.
Okay, so
So it shifted to the left.
By pi over 2.
is it by pi over 2?
Oh, no, by pi over 6.
Oh.
Yeah.
Wait.
Yep.
Because of the 3x.
Right, you got to think about it as factoring out that 3x, right? Right? Isn't that how it works? And now I'm imagining I'm taking this test and I'm like, oh, I wish I would have reviewed this. Why didn't I do this? You told me it was going to be on the test. Okay, I know what I'm going to do. It's either one way or the other. We're either shifting to the left. In one case, we're going left pi over 2 units. In the second case, we're going to go left by how much if you factored out the 3?
Pi over 6.
Right, pi over 6 units. And that would be if you, in other words, if you pulled out the x like this and did your pi over 6. Yeah. Okay, so let's figure out which one it is. How can we figure that out?
Well,
One thing you could do. What's up?
never mind.
Okay.
Probably not.
I'm just looking at the graph that we have right here.
Oh, yeah,
And
we
I
know
notice
plug in.
there's a pi over 6
got
right
it.
there. And so if I shift him over, if I could find out right now, if I shift him left pi over 6 units, right? So in other words, if this one's true, then this thing looks like you've shifted it left pi over 6 units, right? And so that's what happens.
Yeah.
In which case, if I plug in a what, I get out a what?
0,
A 0, you
4,
get
4.
Okay, so let's just try it. Let's see what happens. If I plug in a 0,
You get 4 sine of pi.
I get
Yeah, 4 sine of
4.
pi over 2.
4 times sine of pi over 2. And now, remember, I haven't done that part yet, right?
So we don't need
So what is 4 sine of pi over 2?
0.
sine of pi over 2 is.
Wait, isn't it 0? Oh, no,
Sine
that's
of pi over
cosine.
2 is
Yeah.
1.
So it's 4.
it's 4.
So
Which
it's
works.
looking like this one's correct. Let's just make sure, okay? Because if it were the shift of, if I shift left pi over 2 units, pi over 2 is right here, right? 3 pi over 6 is the same as pi over 2.
Yes.
And so if I shifted it left
Then it'd be at
by
the
pi
negative
over
4.
2 units, yeah, and then I would take that right there, bring him over, we'd have our minimum right there at negative 4. It would come back up and do that. And now I could see if I plug in a 0, do I get out a negative 4? I plug in my 0, I get out a positive 4, so I conclude that's not right. Okay, so this is how you could easily unmess yourself up if you haven't studied. I suggest that you just study and do a bunch of these so that you're not in that situation on the test. But that's how you do it, okay? We factor that out, and that's the shift. After you've factored out whatever this leading number is, the thing that actually compresses and stretches, after you've factored him out, then that's your shift. And so since we know that because we actually studied, we're going to say, okay, then the next thing here is going to be 4 sine 3x plus pi over 2, which means it's a shift,
To the right.
to
To the left.
left by pi over 6, because we factored the thing out. And so I'm just going to do that right now and say, okay. So if I move him, we've already done this, then
It just
he
looks
comes
like cosine.
up to 4. Yep, it looks like cosine. And now I'm just going to keep one period. And so he was at
No, that's
2 pi over 6. He's been moved over one of them. So now he's at 1 pi over 6 and so on. 2 pi over 6. Finally, 3 pi over 6 right there. And meaning that he's where now?
Negative pi.
Negative pi over 6. Okay, so let's say that I told you to graph this on
But we also have to shift it up.
negative pi over 6 up to...
great.
What would be more? So 3 pi over 6, 4,
You go up to 5.
5, 6, 7 pi over 6.
Okay, so one more.
One more. Yeah. Okay, so now we're here. We shifted left by pi over 6 units. Okay. Now, are we done? What else do we need to do?
Shift
Up by 2 root.
Up.
So we just add. To the
But then we have to find a new one.
oh no, we have to find 0.
Yeah. And so, here we go. Let's shift up by that amount. And actually, let's make it easy. I don't want to have to do 2 of these. You could do that. That's like the very last thing you do anyway. We'll just say to 3 pi over 6. Or pi over 2. Whatever. Okay? So, okay, we're going to shift up. Which means... Now, the question is, have I shifted it up so much that he's like above everybody?
No.
Well, 2.
No, because let's
It's
just
less
look
than
at
4.
this.
3 is less
Right,
than
I think that 2 pi over 3 is less than 4. Is that correct? Is root 3 less than 2?
Yes.
Yeah, it had better be, because if I square both sides, I get that 3 is less than 4. And so, yeah, okay, it should be good. Okay, so I haven't shifted him up so much that he has no x-intercepts, but I have shifted him up, right? And so, it's going to look like that, but now the new axis is going to go somewhere in here, okay? We got that?
Yeah.
Okay, so I'm going to draw it where this guy has also come up, like this, has a max right there, comes back down, comes back like that.
Yeah.
This bit right there is at 3 pi over 6. This bit right here is at
4 negative.
2 pi over 6.
Oh,
This bit, which you don't need, I have not told you on the test to label it. Go ahead and label it. It's where?
Where it would have been.
Where, which was where?
Pi over 2.
Pi over 2. Or,
That's not. It's pi over 6. It looks like.
yeah! Look at that. That is a 6. There we go. Pi over 6. And then back here was
Negative pi over 6.
negative pi over 6. Now,
So that's 4 plus.
we
2
need
root
maxima and minima. And so it's what?
4 plus 2 root 3. Whatever that is.
4 minus
Is it 4 minus 2 root 3?
Negative 4 minus.
Negative 4.
Yeah.
Plus this,
Okay.
right? Because the only thing that's changing here is sign. 4 is always 4. This is always 2 root 3. The only thing that changes is I change x is sign. Sign is always, what's the biggest he ever gets? 1. What's the smallest he ever gets, or the lowest he ever gets?
Negative 1.
Negative 1. And so that happens here. Negative 1 times that, so this guy must be negative 4 plus 2 root 3. I think you messed that up on the test before. I was pretty sure. I think you did. I think it was like 4, and then you did, oh, it's plus and minus, because we're used to that, right? Like you see something with a root something, and you're like, oh yeah, plus and minus, right? Not in this case, because that's not what's going on, right? You probably wouldn't make that mistake if that were a 1 or a 2, right? Well, maybe you would. I don't know. But
Wait, isn't that the same as 4 minus 2?
No, 2 root 3 minus 4. It's the same.
Yeah.
It's the same as 2 root 3 minus
4 minus 2
Yeah,
root
yeah.
3. Are you asking me if
No,
this
no,
is...
no.
Let's do it. Let's do
Never
it.
mind.
Plus... Okay, adding, and so I
that
get
means
8
8
is
equals
8 equals to 4 root 3.
Yeah.
So is 2 equal to root 3? Yeah, I think it is. So yeah, you could answer that. 2
So
is
1
equal-
is equal to.
Ah! So yeah. Okay.
That's 3 or 2.
1 is equal to 0. So yeah, none of this matters. Okay, so now, do we have everything? We have a max, we have a min. Oh no.
We need zeros.
We gotta get our zeros. So on this graph, it looks like we only care about 2 of them. Yeah?
So
Okay.
0 for y.
Yes. Okay, good, good, good. So let's do that. I'm gonna get rid of this. I plug in a 0 for y right here, and I get 0 is equal to 4 sine stuff. I'm gonna wait on the stuff plus 2 root 3.
Subtract 2 root 3.
And then divide by 4.
And then take.
And then take.
Divide by
Well,
4,
we don't
which
need
gives
our
me...
sign. Negative 2 root. No, 1/2 root 3.
It's root 3 over 2. Negative root 3 over 2.
Yeah, it's better.
1/2 root 3 times negative 1. Yes, that's true! Well, that is probably the better way of writing it. Okay, now you notice how I called theta theta? Or how I called all of this stuff theta? I think that's probably the best way of doing it. This is how I like to do it. I like to say, alright, hold up, we'll deal with all that junk in a minute. If this were just sine theta, we have negative root 3 over 2. And so we're talking about this thing that goes like this and like that, okay? And so we need to find out where does that happen.
We are just.
And
did
so,
that.
yeah, we just did.
So-
We just did. So we're saying that the output is negative root 3 over 2. And so we have our triangle.
It's pi over 3.
Root
Negative
3, 2, pi over 3. And so this guy gives me a negative root 3. Negative pi over 3. Man, wow. That's negative pi over 3 right there. But also all the other ones, right? Yikes. So what are we gonna do? And so you can see, like, this will get you maybe one of them, one of these guys here, but maybe not all of them.
Oh, well, the other one you can just minus.
So if this one's
Minus.
minus pi over 3, and let's just think about quadrants, right? Because you know that in quadrants the only thing that's over 3 is 1 pi over 3, 2 pi over 3, there's 3 pi over 3, 4 pi over 3, and 5 pi over 3. Just like that, right? And so, okay, if we're in, that's in the fourth quadrant. It doesn't happen again until, here's the first quadrant, second quadrant. It happens again in the third quadrant. And in the third quadrant, it's 4 pi over 3. Yeah?
Yeah.
So then this answer would be at 4 pi over 3. Okay? So hopefully we could get everything we need here. But given that this weird thing has happened, I'm not sure that those are the two that I'm looking for. In fact, it's starting to look like it's going to be 4 pi over 3 and 5 pi over 3 are the ones that I'm looking for. Not too sure, but I'm going to have to use my brain here. And I think it's easiest to just go ahead and say, well, if we do this in general, the same way we did with the other ones, if we find all infinitely many solutions, we've already found 2 of them, right? We found the pi over 3. We could say, in other words, theta equals negative pi over 3 plus 2 pi n. Yeah? And that will get you that one and all of those. The other one is theta equals 4 pi over 3 plus 2 pi n. Yeah? Right? Okay. But it's not theta that we care about, it's that guy. Yeah? So I'm going to replace this and say it's not theta, it's 3x plus pi over 2. 3x. So subtract pi over 2 from each of those, and that gives you 3x is equal to what?
Negative.
Pi over
6.
6.
Wait a second.
Negative pi.
Negative pi over 3 minus pi over 2.
That would be negative 2 pi over 6 minus
Wait,
3
I know.
pi over 6. Which would
Okay,
be
negative 2 pi over 6, 3 pi
which is
over
negative
6.
5 pi over 6.
Negative
Yeah.
5 pi over 6. Okay, so negative 5 pi over 6
Plus 2 pi.
plus
2 pi n.
2 pi n.
So
Okay.
then negative 5 pi over 8.
What about this guy? Yeah, let's do this guy then. 4 pi over 3. Oh,
11
my
pi.
goodness.
Negative
4 pi
11.
over
Yeah.
3 minus pi over 2. And this is
Because it's negative
2, so
No,
8,
it's 8 pi over 8 pi,
over
8 pi.
6. 8 pi over 6?
Yeah.
Minus 3 pi over 6.
5 pi.
Which is
Same.
5 pi
No,
over
it's
6.
not.
But it's the positive one.
Oh. Okay.
Plus 2 pi n.
So then negative 5 pi over 18 plus 2/3.
So now I'm dividing through, and I get negative 5 pi over 18 plus 2 pi. And now, and I'm checking, and I'm like, oh, that was my period, wasn't it?
Oh yeah.
Right? 2 pi over 3 was the period that we found. So I feel like I'm doing this right. That's one thing that's really nice. And 5 pi over 18 plus 2/3 n. So now the question is, okay, well, where is this? Which is 5 pi over 18 between these guys?
Well, the small.
I think so.
Wait.
We're done. Are we?
Let's just see.
Oh, which one's width?
Yeah, and I could tell you that the negative one is not the one you're looking for, right?
Yeah. That isn't,
Negative 5 pi over 18 is somewhere over here.
it's not. Yeah.
And it's probably when this one
But
touches.
you have to add
right there.
1, 2.
Yeah.
Add 2
And
pi.
so what we do first, what I'm going to do is see where 5 pi over 18 is. My guess is it's between here. I'm not sure about that, but my guess is that pi over 6 is between 5 pi over 18, which is between 2 pi over 6. Yours isn't going to be this hard. I'm telling you right now, yours is not going to be this
It'd
bad.
be 3
This
pi
is
over-
really bad.
Okay.
18 is less than 5 pi over 18, which
So
is
what-
less than 6 pi over
If we multiply everybody through by, are you saying
3.
by
Yeah,
3?
Except,
No, they're just the outer 2 by 3.
well, by 3 over 3.
Yeah. So it's like 2 pi
Oh,
over
yeah. So 3 over 18. So 3 times
Six.
2 is 6 over 18.
and then you can
Is that right?
yes.
Ah, we got it. Okay, so this one must be that bad boy right there, right? So this must be 5 pi over 18. Now, obviously, this one doesn't work. And remember, like, we got these by the 2 different sides of, like, regular old sine, right? Like, one of them gave you this one, and one of them gave you this one, which means, like, these 2 are the different ones, right?
Yeah. Oh, right.
And so we are going to need to use both of them to find it. Like, one of them gave you all of the reds here, right? And that was this guy. The other one gives you all the blue points, which was this guy. So it makes sense that now all you've done is you've just stretched it, compressed it, and now, well, the same thing is going to have to be true. Like, you're going to have to get it from there. My guess is that it's the same way that you would get this one. That you take the negative one and add the period to it. So I'm going to take the negative one and add the period to it. In other words, when n equals 1 in this, and we have minus 5 pi over 18
Plus 12
plus, what is it? So that's 2 pi over 3,
Cool.
but you're telling me to multiply the top and the bottom by 6?
Yeah.
Yes. So that's 12 pi over 18. So that's 7 pi over 18? Is that right?
Yeah.
And I'm so done with this problem, I'm not gonna check. It looks right, doesn't it?
Yeah.
Like,
That's right.
it's gotta be right. And if we wanted to, we could try it and go, okay, is that true right there? Is this true?
And it is, yeah. 'Cause
And it
it's-
is, yeah. Just like we did before, right? Okay? Boy, that's ugly. But yours is not gonna be this in depth.
We've done one
It
like
will be
this.
very similar.
Like maybe this exact one, or one very much like in
Oh
class
yeah,
before.
yeah, very, very, very similar. They're all pretty much the same. It's just when it comes down to this, like when it, oh man, yours isn't going to be that bad, okay? But if you could do this one, this would be a great, something like this to practice on. This would be great. Great thing to practice with, okay? So if you could do this, you could feel very confident that you've studied enough. Okay. All right. Okay. So let's see what we're doing on time. Oh boy. Okay. Finally, vectors. Vectors. Let's say I have 2 vectors. And oh, I don't know. They're this.
It just be 3 negative 1. Yeah. You just add the.
Well, I haven't said. I just said you have 2
I thought
vectors.
you said add.
Oh no! I said you have 2 vectors. You have 2 vectors. How can you tell if these are orthogonal?
Oh no.
So if that's perpendicular, right?
That means perpendicular.
So
Um,
we could graph them.
And you think, yeah, but what if I gave you this?
No, there's
Like, what if it was
oh.
2.0703 and 1.02119?
It was.
And then it's like, you're not going to graph that and have it look accurate. Because it might be
dot
off. Like, it might be off by just like a
90.001.
fraction.
Yeah.
Exactly. It might be that the angle between them is like 89.99997 degrees, and by graphing it, you'll never figure that out. There is a very easy way. It's the dot product.
Is equal to 1, right?
1?
If the dot product is equal to,
To 1, right?
1. 9.
let's just compute the dot product and see what this is.
Okay.
2,
2 times
1
plus,
plus 1 times negative 2.
and what does that equal?
Oh, 0. If the
You
dot
better
product-
remember this
okay.
for the rest of your life, that 2 vectors are orthogonal if their dot product is 0. They are perpendicular to each other if their dot product is 0. That is one of the most fundamental important things you could remember for anything involving vectors. It is like the thing about vectors, okay? And that's all you need to show. If you want to show that something is orthogonal, just take the dot product. If it's 0, they're orthogonal.
For
Easy,
parallel, is
easy
it equal to 1?
I think so. No. Not even.
It has to be exactly the same.
They would have to have the same, well,
Oh,
their
okay.
lengths.
Yeah.
Their lengths
Their
would have to, yeah. And so no, it does not work like that. Okay, so that's very important. What else are you going to have to know about vectors? Well, you should be able to convert them to polar coordinates, right? So in other words, any vector, let's take that one,
Cosine,
2, 1, whatever, I don't care. However you want to do it. Here's 2, 1. Okay, here's the vector A.
Oh.
But this corresponds to a point. In other words, the point 2, 1. And we could convert that from Cartesian into polar, yeah?
Yeah.
You better be able to, okay? I'm just, we're not going to go over it. You better be able to.
So,
Finally.
oh, I know how to do that. Yeah.
Are you graphing polar coordinates?
Nope.
Thankfully.
Flowers.
Now, there's one more thing. One more thing
Sine of
we
100
have to
thing.
talk about.
Or R equals sine of theta.
Let's take 2 vectors, and let's do A and B again. A is equal to, I don't know, how about 1, 1. And B is equal to, let's go 1/2. How about -1? Find the angle between A and B.
Oh, right. So,
What would you do?
graph them.
Oh, and you might be able to do it.
Well,
When-
just to get a picture.
Maybe, yeah. Oh, no, so that's a good idea. That is a good idea to say. Okay, here's A is 1, 1. B is 1/2 -1, so it comes down like this. And so you could kind of estimate. That's too far. 1/2 -1. So there's A, there's B, and you could get a good idea of. Okay, well, it had better be like bigger than 45 degrees, right? Whatever you get here, okay? And so that gives you a good idea. How are you actually going to figure it out, though?
Convert them to polar.
No. You could.
What does that help?
Oh, you guys.
So
Well,
you
we
take
need
Guys!
the angle underneath them.
Wait.
That the
No, that's equal
angle
to-
between them is equal to arc cos of
Oh, the dot product over 2?
the dot product
Oh.
over.
Not 2.
Oh.
Oh,
Uh.
I don't know.
Oh, the magnitude of each.
Yes. This is huge. This is huge. This is huge. This is huge. Okay, like I cannot tell you how helpful this is. And
Oh.
I'm gonna so let's just do this real quick and see if we can reduce it. What is A dot B?
So 1/2 plus -1.
Mm-hmm. So 1/2 plus -1, which is
-1/2.
-1/2. And now what's the magnitude of this guy?
1. No, root 2.
No.
Root
It's
2.
the square root of
So yes. So first off, yes.
1 squared plus
Any
1.
vector. Now you guys had better pay attention to this. What I'm about to write right now. Otherwise, you're probably going to be hurting. I don't care how many entries you have in a vector. Let's say we have n of them, or 12 of them, or 700 of them. then the magnitude is always the square root of the sum of the squares. Okay, you just add up the squares. Doesn't matter how many of these guys you have. That's how it's defined. Okay, it could be 3 entries. It could be 4 entries. It could be 20 entries. This is what that is. Okay. Ditto with the dot product. If your B is a bunch of them, like B1, B2, all the way up to Bn, where n is like a million, whatever, as long as they're the same length, then the dot product, I've said this in class before,
Yeah.
okay, right? A1, B1 plus A2, B2. You just add up all of the components. You multiply each of the components together and add them up, okay? And so then, okay, what's the magnitude of A?
No,
one-
it's root 2.
Root 2, okay? Now, what's the magnitude of B, I guess?
5, 4.
Yeah.
Root 5.
Okay, so that's, yep, root 5/4, which we could write as root 5 over 2.
Okay.
So we have a root 5 over 2. I'm looking at this, and it does not look like I can reduce it. Yeah, and so I'm saying, okay, here's arc cos. That guy comes up into the numerator, kills the 2, and so I have a negative 1 on top. Root 2 times root 5 is root 10. Can we figure that out?
No.
No? So, in other words, this one's not computable.
Yeah.
But if it were something else, if it were like root 3 over 2, you'd be able to compute it, right? But in this case, we can't. Okay? Listen, guys.
And then we just basically, it's like the same problem. You just do everything that we've learned so far with sine.
What?
Wait, aren't we?
No, then we're done.
We're
That's
done? Oh,
that's
that's
it.
it?
We're done.
Yeah, it's just the angle between them.
Oh.
We're just asking for the angle between those two, and that was it right there.
Oh.
This is how you find it.
Yeah.
You should, if you don't believe it, go back and either rewatch the lecture or go through the book and do the actual proof yourself if you need to. Like, this is always the case. This is always, always, always the case. No matter if this is, if this vector has 2 entries, or 3 entries, or 4 entries, or 5, or 6, or n entries. This is always going to be the case. And I can tell you right now, I will promise you, you will not be able to graph the ones that I give you for this problem. It will be, I can tell you, it will be impossible for you to visually represent the 2 vectors I'm going to give you.
It's like a smiley face.
No, I'm telling you that
But
you
literally can't.
will not be able to draw it.
Oh.
Like, it's impossible for you to draw.
Like could does instead of 1 it's a smiley.
So, you'll see. You'll see on Thursday. The thing is, it's a super, super simple problem if you do this.
Oh, it's just.
So, my point is this. Like, and I really tried to beat this home in class, and it was kind of like, you know, I'd rather just draw it out. Like, and I understand that, right? Like, I am not a fan of, memorize this formula and then plug stuff into a formula. I hate that. I really hate that. And I would suggest that if that's how this feels for you, if you don't know where this comes from, maybe not so much now because you're studying for a final, but afterwards, be able to derive this yourself or see where the derivation comes from, because this is going to be a big thing in the future. But for right now, like, like, you're at a point where you could, well, what I saw was like, even with this, you know, I would see stuff like this, like here's one of the vectors, right, like a 1 and a 3, or 3 and a 1, a 3 and a 1, and then the other one was like down here with like a 1 and a negative 2, and then it was like, okay, well, if I find this angle here, here's phi, and if I find this angle here, let's call it alpha, then I could say that theta is phi plus alpha, and we're good to go. And so you do your trig stuff, and you say, well, that would be arc tan of this over this, which would be 1 over 3. That's going to be my phi. And my alpha is going to be arc tan of opposite over that is 2 over 1. So arc tan 2 over 1 is just 2. And so then, okay, you got your answer, and that's great. But what happens when it's like this? Right? So one of your vectors is, I know, we're so close. One of your vectors is this guy. And the other vector is back that way, this guy. And you're looking for this angle.
And if you have 4 dimensions, you couldn't even do it.
It's almost as though in 4 dimensions you wouldn't be able to draw it.
Yeah.
Oh.
Huh.
Oh no.
But if you did that, it would be really, really easy, right? Because you just, okay, dot product, divide by that, arc cos, do I know what that is? Is it a 1 over root 10, or is it like a root 3 over 2? Oh, it's root 3 over 2. Well, I can find what that is, and then you get pi over 7, or whatever it is. Or I guess not pi over 7, but you know what I mean, okay? Everybody feeling me on this?
Yes.
Okay, guys, I think that's everything you need. I'll tell you again on Thursday. Problem 6 is the last of the problems. Save it for the end. It has 4 parts to it, and do them one at a time.
Is there an extra credit problem?
There is an extra credit problem. But I'm just telling you, if time is becoming an issue, then like just leave that one for the last. And it's a little bit intricate. It's just you don't worry about that one. Like if you're skipping around and doing stuff, save 6 for the end, just because.
Okay.
Okay, guys.